Hello everyone. Today's video is about linear combination of vectors. This is a new operation that we can perform with vectors which we are not used to when we deal with numbers. So this is new and it belongs to linear algebra. How does it work? If I give you a set of vectors, u1 all the way up to uk, and a set of scalars, I remind you that a scalar is a real number, then the linear combination of vectors u1 through uk with coefficients c1 and ck is the following vector. It's a vector that I get by rescaling u1 by the scalar c1, and then I add that by a rescaling of u2 by the scalar c2, and I do that with all the others. So it's a way to combine vectors u1 through uk, possibly after rescaling them by a constant factor. That's why it's called the linear combination. It's a combination of the vectors, and it's linear because every vector appears without exponents. That doesn't even have meanings with vectors, but that's what happens. Okay, let's try to see this in practice. Here's a few vectors. I want to check that the vector 5, 4 is a linear combination of the vectors 1, 2 and 2, 1. How can I check that? Well, if it is true, and that's what we want to make sure of, I can write 5, 4 as a linear combination of vectors 1, 2 and 2, 1. In other words, I can find scalars a and b such that that equality is satisfied. Let's try and see how this translates into a set of linear equations. That equality is satisfied only if we can find a solution for 5 is equal to a times 1 plus b times 2, and 4 is equal to 2 times a plus 1 times b. I'm taking each entry of these vectors and writing out this equation just for that entry. And then I need to solve these. This is a linear system of two equations in two variables. If you solve it, you'll find that there is a solution, and the solution is equal to getting a equal to 1 and b equal to 2. Since there is a solution, this means that 5, 4 is indeed a linear combination of 1, 2 and 2, 1 with the following coefficients. 1 in front of 1, 2 plus 2 in front of 2, 1. Let's try a similar thing, but this time we use different vectors. So this time the question is, can we write 5, 4 as a linear combination of the vectors 1, 2 and 2, 4. Writing this out in equations, entry by entry, we get that 5 has to be equal to a plus 2b, and we get that 4 has to be equal to 2a plus 4b. If I take this second equation and divide it by 2, I get that 2 is equal to a plus 2b. But now I got that 5 is equal to a plus 2b equal to 2 by combining the two equations and setting 5 and 2 equal to one another because they're both equal to a plus 2b. This is no solution. And this means that 5, 4 is not a linear combination of 1, 2 and 2, 4. We can give this example a geometric interpretation in the following way. So let me draw everything. That's what's written here. See, the first case is what we had here. We have the vectors 1, 2 and 2, 1. And we said that we can write 5, 4 as a linear combination of these two. In particular, we may double the vector 1, 2 and get something like this. And then we may add to that vector, sorry, we may double the vector 2, 1, and then we may add the vector 1, 2 to that. In other words, what I'm saying is that we can construct a parallelogram whose edges are multiples, scalar multiples of 1, 2, and 2, 1. This point here is twice the vector 2, 1. But you see that we can't replicate the same thing here in this case because 1, 2, and 2, 4 are on the same line. So they cannot span anything that is outside that line. There is no way that we can rescale them and add the scalar multiples together to get something that is off that green dashed line there. That's the summary that is written here. If we have two vectors with two different directions in R2, then we can write any vector as a linear combination of them. We can always take a multiple of them and rescale it accordingly so that then when we sum them, we get any vector we want. In this other case, we have the system of equation that I rewrote like this: 5, 4 is equal to a plus 2b times 1, 2. If we move up here, you should notice that this 2, 4 is nothing but twice the vector 1, 2. This system has no solution, and that corresponds to 5, 4 not being on the line spanned by 1, 2, and 2, 4. Okay. The last topic that I want to mention in this video is that of standard vectors. These are vectors that are very important because we can use them to write every other vector as a linear combination of these standard ones. Let me just write this in an example. If I have a vector v, which is given by components a, b, it's drawn like this in the plane. And let's suppose that I have my two standard vectors, E1 and E2. Those are the vectors whose components are 1 in the first entry and 0 in the other, and E2 is 0 and 1. So I drew E1 here, and I drew E2 here. Then this vector over here is A times E1. And the vertical vector over here that reflects somehow the component of V is nothing but B times E2. What I've been writing there is that we can write V, which is AB, as A times E1 plus B times E2. Or more explicitly, A times 1, 0 plus B times 0, 1. So we can always decompose every vector in a linear combination of standard vectors. And of course, standard vectors exist in every dimension. Here's a little sketch for how the standard vectors look like in 3 dimensions. Each one of them is a non-zero entry in one of the corresponding indices. And they look like this on the system of 3 axes. But nothing stops us from having a set of standard vectors for every dimension. And they all look the same. E1 will be the one that has a 1 in the first entry and 0s otherwise. E2 will have a 1 in the second entry and 0s otherwise, and so on and so forth. That's all for linear combinations of vectors and special vectors. I'll see you in the next video.